All right, so if we think about the decimal 0.025 repeating, that is 0.025, 025, 025, etc. So I want to write that as an infinite series using summation notation. So first I'm just going to write it as a sum without summation notation. So 0.025 repeating is actually equal to 0.025 plus 0.000025 plus 0.0000025 plus dot dot dot. All right, so if I wanted to put that into summation notation, I start with 0.025 and then I multiply each time by 0.001. So I'm going to do that to the n, and then I'm going to start my n values at 0. That way, when I plug in my first n value, the 0.001 term is 0.001 to the 0, which is just 1, and I get my 0.025 as my first term. And then when I plug in a 1, 0.001 times 0.025 gives me 0.000025. And I'll do that to infinity. Right? Or if you like to start at n equals 1, you could have n equals 1 to infinity of 0.025 times 0.001, but then your exponent has to be n minus 1. So my first four partial sums, remember a partial sum is the sum of the first of several terms. So S1 is just the first term, which is 0.025. And S2 is the sum of the first two terms, which would be this plus this, which comes out to 0.025, 025. And then S3 is going to add the third term, which is 0.025, 025, 025. And S4 is 0.025, 025, 025, 025. So to prove that this sequence of partial sums converges, you could either say it is increasing and bounded above, right? We know that this thing will never get bigger than, say, 0.026, which implies that it must converge. Right? This thing is always increasing, but bounded above means it must converge. Or you could say it's geometric, and my multiplier r is 0.001, which is less than 1. And that tells you also that it converges. The exact sum of the series as a rational number I can use the formula for a geometric series. So a geometric series with r less than 1 converges to a over 1 minus r. The first term of my series is 0.025. My multiplier is 0.001. So this is 0.025 over 0.999, which is 25 over 999.